Okay, there are a series of numbers that we want to consider, and we want to consider whether these numbers are natural, integers, rational, real, and we want to consider that for every number. Okay, just briefly, natural numbers are the numbers you use to count with. Back when I was very young, when we just invented numbers, we only had numbers 1, 2, 3, 4. All we used numbers for was to count sheep or weapons, and we had no need of other numbers. So just the numbers 1, 2, 3, 4, etc. Integers. Of course, now there's whole numbers. So we had a big controversy. Several members of my clan got killed off because they insisted, well, if I've got 6 sheep and trade you those 6 sheep for 12 spears, then I have 0 sheep. And they said, no, you don't have 0 sheep. 0 is not a number. You just don't have any sheep. What's this 0 thing? And then spear in the throat, you know. So, you know, that was very controversial, sort of tragic, but we eventually reconciled it, and people realized there wasn't any harm in talking about 0. Then we started thinking about, well, okay, if I got 6 sheep, give you 1, I've got 5. I give you another one, I got 4, and so forth. And then I got 0, and people, you know, started to get okay with that. Then somebody said, okay, now I don't have another sheep to give you, but eventually I will. So it's like right now I have -1 sheep, and another big war, you know, slaughter. It was terrible. But we eventually started to realize that those negative integers, those negative numbers had some meaning. So the integers are the set of natural numbers expanded by 0 after much bloodshed, and then expanded into the negatives. So the negatives of all the natural numbers are included in the integers. Rational numbers, now these came about, you know, they weren't very controversial, because, you know, we split a sheep. We split it down the middle. Everybody's got half a sheep. And then we started quartering it, and sometimes, you know, somebody would do a trade and get 3/4 of a sheep instead of just half a sheep or a quarter of a sheep. So rational numbers, that's integer over integer. And that was okay. And, you know, once people accepted negative integers, they accepted negative fractions as rational numbers. So any integer over any integer became legal, although some people still thought that negative rational numbers were pretty weird. And then I didn't list irrational numbers here, but the problem listed irrational numbers. Irrational numbers are the numbers that aren't rational. Now, for a long time, everybody figured that rational numbers would be the whole picture, because if you draw a number line, you pick any point on that number line, and you start subdividing the number that point lies between into smaller and smaller increments. You can get as close as you like to that number, and people figured that, well, if we haven't divided it enough, but if we divide enough, we can get to any number. Then things got ugly again when somebody came along and proved that square root of 2 couldn't be done by subdividing intervals of the number line. And it's not a rational number. And so there are irrational numbers. And then people were getting a little more reasonable, so eventually they got convinced that there were actually, in a sense, there are infinitely many rational numbers, but there were also infinitely many irrational numbers. And not only that, but the infinity of the irrationals is bigger than that of the rationals. So, and that took a little getting used to. Not everybody understands why that is, because it takes a little bit of work to get there. And then we put all the rational and irrational numbers together, all these numbers together, to get the real numbers. Just a little more on the thing I was talking about with subdividing intervals. I got this much of the number line, 0, 1, and 2 here. if I want to locate 3/4, that's pretty easy to do. I just cut the interval between 0 and 1 in half, assuming I have a way of accurately cutting it in half. And then I cut each of those intervals in half. So now I have 4 intervals, and each of these intervals, each of these distances, then we think of as 1/4. So here is 3/4. And we could do that for fractions with larger denominators, but of course, the bigger the denominator, the more times we have to divide up this interval. Now, square root of 2 lies between 1 and 2, and that's easy to prove because 1 squared is 1 and 2 squared is 4. And 2 lies between 1 and 4, so the square root of 2 has to lie between 1 and 2. It turns out it lies a little to the right of 1.4, so we could subdivide this interval into 10, hopefully more or less equal parts. That one got a little too big, but we do that. And then we could locate 1.4 easily. It's just right here. If you square 1.4, it's 1.96, a little less than 2. So we know that the square root of 2 has to be a little bit to the right of 1.4. So the square root of 2 is maybe about here. The problem is, and it can be proven, that if you can't actually locate the square root of 2 by subdividing. So you never know exactly where it is. You can never actually locate it. Okay, I could subdivide this thing 100 trillion times, and none of those subdivisions would lie on the square root of 2. You might say, well, what if you did 100 trillion and 57? That would put the divisions in different places. Still, it wouldn't work. No matter what number we divide this interval into, no matter what number of subintervals we divide this interval up into, we are never going to locate square root of 2. So 3/4 is rational. 1.4 is rational. Square root of 2 is not rational for reasons that we probably won't try to prove, although we could.